begin by examining a function that we know, 1 over x. And what we're going to do is we're going to create a table of values, and we're going to see what happens as the values of x get really, really large in the positive direction, and as the values of x get really, really large in the negative direction. So let's begin by working in the positive direction. Obviously, if we put in x is equal to 1, we get 1 over 1. So f of x is equal to 1. If we put in x is equal to 10, we get 1 over 10, which we know is a decimal number as 0.1. If we were to put in something like 1,000, we would get 1 over 1,000, which is this decimal number. And I'll do one more. Let's do 100,000. So 100,000. We want to take a look at our y values, our f of x values, as these values of x get increasingly bigger. Now it looks like these y values are getting really, really small. So let's see what's happening over on the other side. So let's begin with negative 1. Here we'll have 1 over negative 1. Next, maybe we'll try negative 10. This is going to be negative 1/10. Then maybe we could try negative 1,000. So here's negative 1,000th. And we'll do one more, we'll do negative 100,000. And we'll get 1 over negative 100,000. So again, we see as we start making our values of x get bigger in the negative direction, our y values, our f of x values, are also getting closer and closer to the number 0. So this slide is summing up what we saw on the last slide. And that is that our y values, our f of x values, tend to get really small as our x values get bigger in both the negative and the positive directions. And this shouldn't be a surprise if you recall what our function 1 over x looks like. So I've drawn a rough sketch here of the function 1 over x. So we see here as our x values get larger in the positive direction, our function starts to decrease, and it gets closer and closer to the line y is equal to 0. Now we have the same kind of action over on the left-hand side, where as our values of x get larger in the negative direction, our y values tend to get really close to 0 in the negative direction as well. So what we have overall in red is we have a horizontal line here, and we're going to call this line in red y equals to 0. So our function gets really, really close to this line, but never quite touches this line as x gets really big, and as x gets really big in the negative direction. So it's that last slide that leads us to the definition of a horizontal asymptote. We say that the line y is equal to b is a horizontal asymptote of our function f of x if our function approaches that line as x approaches plus or minus infinity. So in other words, this means as x gets larger in the positive and negative directions. So relating this back to our function 1 over x, we say that y equals 0 is a horizontal asymptote of our function 1 over x because our function approaches this line as x gets really, really big in the positive direction, and it also approaches this line as x gets really big in the negative direction. In this example, we're going to try to determine the horizontal asymptotes of the following rational function. F of x is equal to 2x squared minus 11 all over x squared plus 9. Now, in your calculus course, you're going to develop some ways to figure out your horizontal asymptotes relatively quickly. But for our course, our pre-calculus course, the easiest way for us to figure out the horizontal asymptotes is to do a table of values. Because we know a horizontal asymptote must happen as x gets really, really big in the positive or negative direction, we're going to focus on using large values for x. So let's start maybe with x is equal to 1. Now what I want you to do is take out your calculator and follow along with me. If we plug in the value of 1, I want you to check that we do get the value negative 0.9. Okay, next we're going to try a value of 100. And if we put in a value of 100, we get 1.997. And there's more digits after that, but I'm just going to focus on the first three. And if we were to put in a value of 1,000, we would get 1.999 with more digits. And you can even go one more, so 10,000 again would give us 1.999 with a bunch of digits. So we see that as x is getting really, really big, our function is tending towards the value of 2. Now let's see what happens in the negative direction. So let's start with negative 1. And again, you can double check that that is going to give us a value of 0.9 by using your calculator. Then maybe we'll try negative 100. Negative 100 should give us a value of 1.997 with some other digits. Then maybe we'd try negative 1,000. And negative 1,000 should give us 1.999 with some more digits. And we could even do one more, negative 10,000. And again, we should get 1.999 with some more digits. So again, we see if x is getting very large in the negative direction, then our function again is tending towards y is equal to 2. So just to summarize everything, we might say as x goes towards infinity, f of x goes towards a value of 2. Similarly, as x goes towards negative infinity, f of x goes towards y is equal to 2. So here we can conclude that the horizontal asymptote of our function f of x is y is equal to 2. Instead of figuring out what happens as x gets really, really big in the negative or positive directions, let's see what happens as x gets really, really close to the value of 0. So let's again start with the value x is equal to 1. If we were to substitute this into f of x, we get 1 over 1. Now let's go down to 0.1 or 1/10. 1 divided by 1/10 is equal to 10. What if we try 1/100th? Well, 1 divided by 0.01, this is going to be 100. And we could keep developing this pattern. So let's say we divide next by 1,000th. This is equal to 1,000. And you can see as we get closer and closer to 0, our f of x values are starting to get larger and larger and larger. Now we could do the same thing on the other side of the y-axis. We could start at negative 1. And if we substitute in negative 1, we're going to get a y value of negative 1. So let's make this a little bit smaller. Let's go negative 1/10. 1 divided by negative 1/10 is equal to negative 10. And let's continue on this pattern by looking at negative 100th. 1 divided by negative 100th is negative 100. And we could keep going. So here is 1,000th. So here's negative 1,000th. And if we do that division, we get negative 1,000. And of course, if we do negative, how many zeros do I need? There we go. So negative 10,000th. And if we do that division, we of course get negative 10,000. So similar to what we saw in our other chart, as we get closer to 0 in the negative direction, or on the left-hand side of 0, our values of f of x get really, really big in the negative direction. This slide is intended to summarize our findings from the last slide. If you recall the function 1 over x and what it looks like, we have it here. And what we're doing is we're trying to see what happens as our function gets closer and closer to the x value of 0. So as x is coming in closer to 0 on the right side, or from the positive direction, we saw that our y values started to get bigger and bigger and bigger. And we also saw that as x got closer to 0 from the negative direction, or the left side, our y values got smaller, I guess, or bigger in the negative direction. So this leads us to think that something is happening around this dashed red line here, x is equal to 0. This leads us to the definition of a vertical asymptote. We say that the line x is equal to a is a vertical asymptote of our function f of x if f of x approaches positive or negative infinity as we approach that line from either the right or the left-hand side. So recall, for our function 1 over x, something funky was happening around the line x is equal to 0, because as we approached x is equal to 0 from the right, our y values skyrocketed to positive infinity. And as we approach x equals to 0 from the left-hand side, our y values also skyrocket, only this time they skyrocket to negative infinity. So we say that x is equal to 0 here is a vertical asymptote of 1 over x. The nice thing about vertical asymptotes in our course is that we can talk about vertical asymptotes without having to create a table of values to consider what's happening. Vertical asymptotes always follow the following rule. If we have a rational function, the vertical asymptotes of that function are going to happen when the denominator is equal to 0. So what we saw in our case for the function 1 over x was we had a vertical asymptote at x is equal to 0. So what might happen if we have something a little bit different, like g of x as 1 over x plus 3? Well, what we could do is we could take x plus 3, figure out when that is equal to 0, and that's going to tell us that there's a vertical asymptote at negative 3. And this leads us to the big idea here, and that is if we have a rational function where our denominator is more complicated, what we can do is we can factor the denominator and try to figure out when each of our factors is equal to 0. That is going to help us find every single vertical asymptote of our rational function. In our last example, we want to determine the vertical asymptotes of the rational function 5x plus 2 all over 2x squared minus 13x minus 7. Now where we want to start, remember, for vertical asymptotes is inside the denominator. We want to set this denominator equal to 0. Since this is a quadratic expression, we're going to have to try to factor this. So let's try to do that using trial factors. So here's 2 and 7, nice prime numbers, so it shouldn't be too hard to figure out which ones make up 13. It looks like if we use the top two, 1 and 14, we can get a 13 out of that. So we can factor this into 2x and x. And we need our 2 to be multiplied by 7, and we need to have a negative 14 plus 1. So this tells us either 2x plus 1 is equal to 0, or x minus 7 is equal to 0. The second one's pretty easy to solve. We get x is equal to 7. The first one, we can subtract 1 from both sides to get 2x equals minus 1, and then divide by 2 to get x is equal to 1/2. All of this work tells us that this rational function has two vertical asymptotes, one at x is equal to negative 1/2, and one at x is equal to 7. Alright, my little epsilons, stay positive.